Hello everyone, let's go ahead and take a look at similar figures. Now, if I was to go ahead and show you this yellow triangle and this blue triangle, and I ask you, are these two shapes similar to each other? Now of course, you would probably look at them and you say, wow, yeah, they look kind of similar to me. And I think for the most part, people generally have a sense that if two shapes are similar, they have the same shape, but they're just a little bit different in size. Okay, from a mathematical perspective, we need to be much more precise and accurate. And in order to test for similarity, there's a couple of things that we can do with these geometric figures. For example, one of the things that we can do is we can guarantee that at least two of the angles, let's say for example with triangles, and we'll just limit ourselves to triangles at this point, that you have two angles that are actually equal to each other. So let's go ahead and see. If I were to take this angle, this triangle here, and if I was to put it right on top of that, hey, sure enough, angle F and angle C are exactly the same. If I was to go ahead and put angle A and angle D on each other, sure enough, they're exactly the same. And notice that I don't need that third angle. And of course, the reason for that is that if we know that this angle and this angle, this angle and this angle, those two angles are exactly the same, being that the sum of the interior angles add up to 360 degrees, then E and B, of course, must also be the same. So what I know then is that, in fact, hey, these two shapes, or these two triangles in this particular case, are in fact similar from a mathematical perspective. Now, we'll go ahead and take a look at the side, and the side angle, in class. But for right now, let's just go ahead and say that our simple test for similarity, which is angle, has allowed me to mathematically say that these two figures are indeed similar to each other. Now, if we go ahead and say that they are similar to each other, we use this notation. It's kind of like a single wavy line that says that this triangle here is similar to this triangle here because of the angle test for similarity. Okay, now let's come back to what we have here from a mathematical perspective. Now that we know that these two triangles are indeed similar, we can say now that these two shapes are similar because their dimensions are in proportion. Okay, we already tested for similarity. We know that they are similar. Therefore, the dimensions are in proportion to each other. In other words, the ratios between the corresponding lengths are equal. Now, what that means then is that if I go ahead and take a corresponding side and I divide it by another corresponding side to both of these triangles, I'll be able to come up with a proportion that is going to be true. Now, that can be very difficult at times because, let's say for example, in this particular case, it's quite easy to see the correspondence. This length corresponds to that length, this length corresponds to that length, this length corresponds to that length. But oftentimes, it's not that easy because sometimes the figures look like this. And how do you know? Are those two figures similar? If I have it like this and I go like this, are those two figures similar? And sometimes it can get really confusing in terms of how to go ahead and create the proper proportions that will go ahead and describe the similarity of the two figures. Now there's a very easy way of making sure that you can all do that and do it very simply. And this is the key. If your notation accurately describes the corresponding vertices of the similar triangle, in this case we're just sticking with triangles, then creating proportions that are correct is simple. And let me show you how it's done. So say for example, we know that triangle DEF is going to be similar to triangle ABC. Now, the thing that you have to be very careful of is that the corresponding vertices are in the same location with regards to your notation. So remember we said that if I go ahead and take this triangle off again, is that vertice D corresponds to vertice A. And that's why I say triangle A here. So I go triangle D, then E, then F. So that means that I have to start off with triangle A, and then the vertice that corresponds to E is B, and the vertice that corresponds to F is C. So even though I go ahead and switch this around like this, let's say like that and like that, the notation that you use to go ahead and describe the similarity between these two figures, regardless of the way that they're juxtaposed to each other, is going to now allow me to create the proportions that I need to go ahead and show that these two figures are in fact similar to each other. Now, how does that work? If I wanted to go ahead and create a proportion of two sides, a ratio of two sides of this figure equaling a ratio of two sides to this figure, if my original notation that shows the similarity is correct, then creating these proportions are very simple. Take a look. If I go ahead and say DE, the length DE, over EF, so this length divided by that length. How am I going to determine, given the blue one, what lengths I should put in ratio? Now, if I went D to E, then that means that for the blue triangle, I have to correspond that to the length AB. So notice DE, the AB. Notice that DE divided by EF, notice the EF is right here, then that means that the corresponding side of the blue triangle is going to be BC. This proportion is correct. Okay, so I can do the same thing even with different lengths of the triangle. Say, for example, I use DF. So notice DF over EF is going to be equal to, in the blue triangle, notice where DF was, the vertices DF. That means I have to take AC, the length AC, divided by, well, here's EF, and that means that I have to divide it by BC. Okay? And I know now that these proportions are indeed correct. Okay, so let's go ahead and kind of wrap up things. We said that similarity, of course, everybody I think has an intuitive sense of what it is, but we need to be very, very careful and be mathematically precise and accurate by making sure that first we can test for similarity. Once we go ahead and establish that yes, these two figures are indeed similar to each other, we make sure that we go ahead and use the proper notation for similarity to show correspondence between the vertices. Once we know the correspondence between the vertices are correct, then creating proportions between the triangles is going to be very, very simple and straightforward, and you'll always get the right answer, assuming that your algebra is correct as well. Okay, so we will go ahead and take a look at some of these problems the next time that we're in class, and we'll take a look and see how you do. So, good luck. See you next time. Bye-bye.